We start with the toss of a die. It's the oldest, simplest game of chance. But the exact same math governing this physical tumble also powers digital spam filters, fraud detection algorithms, and forecasting systems processing millions of data points a second. Despite the massive difference in scale, both systems operate on the exact same underlying mathematical architecture. Probability theory provides the mechanical framework required for reasoning under uncertainty. This structure was formalized by the mathematician Andrei Kolmogorov, who distilled the chaos of chance into 3 bedrock laws. To move from a coin flip to a functional model, we follow a sequential path, defining the universe of outcomes, quantifying them with counting rules, restricting them through conditionality, and finally updating them with Bayes' rule. It is tempting to treat these foundational concepts as abstract philosophy, but doing so is a technical error for any practitioner. Without this axiomatic foundation, we lose the ability to verify if a complex model's output is a logical necessity or merely a calculation error. We begin by defining the boundaries of our experiment. The sample space, denoted by omega, is the exhaustive set of all possible outcomes. This diagram shows our sample space as a bounding box of possible outcomes. An event, marked by this circle, is just a specific collection of outcomes we care about, a subset of the overall space. This brings us to the first Kolmogorov axiom, non-negativity. In practical terms, this means no event can ever have a probability of less than 0. The second axiom is normalization. Normalization mandates that the probability of the entire sample space occurring is exactly 1, or 100%. The third axiom is countable additivity. For disjoint events, meaning they do not overlap, the probability of their union is the sum of their individual probabilities. We require a different mechanism for events that do overlap, leading to the addition rule. If we simply add the probabilities of 2 overlapping events, we double count the outcomes they share. To correct for this, we subtract that intersection exactly once. Tools like the complement rule exist as theorems derived directly from these 3 axioms, rather than standalone assumptions. Before utilizing continuous distributions, we must be able to count exact, finite, equally likely outcomes. The underlying engine of all counting rules is the multiplication principle for independent sequential stages. A 4-digit PIN code with 10 options per digit, for example, is calculated as 10 times 10 times 10 times 10. We can apply this logic to more complex groupings, such as selecting a 4-person review committee from a department of 12 faculty members. If the internal order of the members does not matter, we use combinations. Using the combination formula, pulling 4 generic silhouettes from our 12 results in exactly 495 distinct possibilities. If specific hierarchical roles matter, we must use permutations to account for that order. If that committee must have a designated chair, a secretary, and 2 generic members, the math changes. We multiply 12 options for the chair by 11 for the secretary, then multiply by the 45 ways to choose the remaining members. This yields a much higher count of 5,940 possibilities. Determining whether an event space distinguishes order dictates which formula is used, leading to vastly different probability estimates. Conditional probability is the mathematical language for updating belief as new information arrives. It asks, what is the probability of event A, given that we now know as a fact that event B has already occurred? Conditioning on B has a physical effect on the math. It discards the rest of the sample space, effectively shrinking the universe of possibilities down to the boundaries of event B. This mechanical shift helps resolve a frequent confusion between independent events and mutually exclusive ones. Mutually exclusive, or disjoint, events are outcomes that cannot occur at the same time. Their intersection is 0. Because they cannot occur together, these events are dependent. If you know that A happened, you have perfect information that C did not happen. Mathematical independence is a specific property where knowing one event yields 0 information about the other. It's a result of the math, not a default state. In practice, the probability of an event usually relies on hidden underlying states. To model this, we use a partition, splitting the sample space into mutually exclusive and completely exhaustive pieces. The law of total probability allows us to compute an event's likelihood across all these partition states. We build the total probability by calculating the event's likelihood within each specific column, weighted by the size of each piece, and summing them together. This process links back to our definition of conditional probability, applied piece by piece across the partition. This total sum provides the denominator required for complex inference. This law allows us to eventually invert the direction of conditioning through Bayes' rule. Consider a scenario where a rare disease affects exactly 1% of a population. A diagnostic test for this disease has 95% sensitivity, but carries a 10% false positive rate. If a random patient tests positive, what is the actual probability they have the disease? Intuition often focuses on the test's 95% accuracy, ignoring the rarity of the condition. Bayes' rule forces a disciplined combination of the new evidence with the prior reality of the diseases. Mathematically, the patient has just an 8.8% chance of having the disease. The volume of false positives from the healthy population outweighs the rare true positives. This is the base rate fallacy, the error of conditioning on the likelihood of evidence while ignoring the prior base rate. Building from Kolmogorov's axioms through counting and conditionality leads to Bayes' rule, a method aligning human intuition with the mathematical requirements of evidence and probability.